It's been a long journey, the last 25 years or so. So back in the last century, we were calling hybrid event beds sandwich beds, which now, if you Google sandwich beds, you get strange images like this one at the bottom. Terminology has moved on, I'm glad to say, because I don't think sandwich bed was a particularly fantastic terminology anyway. And as has our understanding and our application of that understanding in the subsurface. So I wanted to deliberately here to show a few nice choice pieces of core from around the world that I've personally got to work with. So there's a series of what Jill and I would call confined or classical or sometimes Hortonian hybrid event beds. Examples from Denmark, Norway, and the UK. And then down the bottom here, more slurry type facies, low type kind of hybrid event beds in what we would consider to be relatively unconfined systems from the Paleogene Gulf of Mexico, some from Malaysia, and another example from the UK. Come on, advance. There we go. So we did a little bit of thinking about the kind of the research trends that have been going on surrounding hybrid event beds, but we particularly wanted to think about it from a subsurface perspective because we work for oil companies. And as much as there are hundreds of papers about hybrid event beds, there are relatively few that have been published that are kind of exclusively tilted towards industry data sets. And that's understandable because most of what we derive is from outcrop or from core. So one of the first brilliant studies was back in the 2000s on the Forties system and the Britannia system in the UK because they had large core data sets. More recently, there's been work done in the Gulf of Mexico on more unconfined systems of the Wilcox. Some very nice papers there, but relatively little actually released. And this is partly a function of the fact that as these fields have developed, they've gone from being all about the geology to more being about engineering, which is unfortunate for our understanding of hybrid event beds in these kind of systems. But I would say to you that if you're in academia, there is probably a whole bunch of data there that you could access and that would be a very good data set. Then more recently, there's been some nice emerging work, and Peter showed this very same piece of rock in his presentation this morning, coming out of the US and Canada onshore unconventional systems, where thankfully we have more data, it's cheaper to acquire. And there's some important work to understand, such as in the Wolfcamp, hybrid event beds can either be baffles or barriers depending on pertaining reservoir conditions. So again, I would say that that's a kind of a potential rich area of research for those of you working in academia. At this point, I'm going to turn it over to Jill.
Okay, so from our experience in terms of reservoirs, the HEBs we have studied have shared properties in grain size, and one of that is that basically silt is a very high percentage in HEB reservoirs, and often clay is not particularly elevated. And I want you to hold on to that thought to the next slide. It's silt and not clay that degrades the reservoirs. So the permeability of most hybrid facies, not the H1 particularly, but the rest, is low for a given porosity, and you can see this on the graph presented by prepared by Andy Pullum. And so, in his words, sorting matters. They are high in carbon, as Peter has mentioned, and also in platy ductile components, micas and lithic. They're spatially extensive in distal settings of all systems, and in time, HEBs are very common in retreat. Let's look more closely at the silt problem. For a given porosity of 18% here on the top graph at the left, the permeability varies by 2 orders of magnitude in our reservoirs. The plots in the bottom left show the dramatic effect of silt percentage on permeability with relatively little effect on porosity. And we have found in our experience, porosity logs like regular gamma are absolutely no use for identifying HEB prone intervals. What logs can we use? Well, silt here works in our favor because of the high surface area of silt grains. It raises the residual water saturation of HEBs and makes them detectable on resistivity and micro-resistivity logs, and Stan will talk a little more to that. They're also detectable on NMR logs. Point counting the mineralogy for each grain size revealed another surprise for us, that the ductile components, the micas, the lithics, are actually in the rock framework, the coarser grain fractions, not in the finer grain sizes. The silt is dominated by rigid materials like quartz and feldspar, and this has an effect on the acoustic seismic properties and accounts for what we observed, which was lower shear velocities of HEBs. In other words, the framework itself is wobbly. Okay, so now we're going to distinguish two end members, and we're open for both critique and debate on this. We're going to have a look at what we call the confined and the rather coarser grained in our experience Annot type HEBs, and then contrast them with relatively unconfined systems. And the confined ones are rich in classic linked debrites, particularly those that are H3 prone. The debrite portions are rich in clasts of thin-bedded strata and often with fragments of remobilized units as well as mudclasts. Spatially, these HEBs are abundant close to onlaps or predicted onlaps within subbasins, as borne out by Ewan Sutter's observations in the case example in Annot at Bro. In time, this form of HEB tends to occur in the first order growth and retreat cycles of basin fill, and at a higher order, they dominate the retreat facies associations. So why are they particularly prone in the retreat? Well, in a confined system, the distal facies belt is often forced to back up directly over the growth part of the cycle. And the reason for that is the structural confinement actually prevents avulsion. In retreat, the sediment flux to the deep water drops, and relatively speaking, structures continue to grow because they have a longer time wavelength than the changes in sediment supply. So structural relief, like on salt highs or thrust terrains, and steep basin margin slopes become prone to failure. And the turbidity currents still entering the basins ingest the available debris close to that steep basin margin. That is our hypothesis. Whoops, I've just given myself a shock. Right, so now to the other end member, the finer grain Wilcox type HEB, so-called because they dominate so much of the incredibly extensive Paleogene reservoirs in the US, Gulf of Mexico. So we here have banded H2 facies all over the place, more massive and in addition, an H1 facies that is massive but very low permeability, often misidentified as regular high-density turbidites. They dominate the Eocene reservoirs in the ultra-deep water US GOM, and you can see here on Ian Kane's published core photographs of oil-bearing reservoirs, the good quality turbidites have a bright UV on the left, and they degrade towards the right as the silt content increases, the residual water saturation increases, and the UV glow parallels the drop in permeability. It can drop so far that people will identify these as water-bearing reservoirs and quite often put perched water contacts in on logs, just because we're entering a very high HEB facies. They're rich in lithics, they're spatially extensive, and in time, characteristic of first-order initiation at the basin scale level. In other words, very high sediment flux systems and a lot of available unconsolidated muds and silts at the distal limits of the system available for rapid ingestion, much along the lines of Jacobas and Iris Verhagen's experiments. And so finally, and perhaps most importantly, in the subsurface, we need to be able to upscale any observations we make in core. Facies to facies associations to genetically related architectural elements. And when we did this systematically, and this was in the Wilcox itself, or what I call the Paleogene, patterns began to drop out, and the channel and the channel lobe transitions had the best reservoirs. The lobe fringe, and they're here in yellow on the left-hand graph. The lobe fringes, as we all expected, on the right-hand graph here, were worse in both reservoirs. But the lobes are a real mixed bag. The lobe axes remained okay, but higher in the stratigraphy, as we went up into the second order retreat, the actual lobes themselves became as poor quality as their time equivalent lobe fringes. And these results actually parallel those of Gardner's research team in Brushy Canyon. In other words, the lobes are now dominated by HEB fascies, be it at H1 poor quality or H2 fascies, banded. Okay, over to you, Stan.
Okay, so as you can tell, we're trying to cover a lot of ground, and now we're going to ask for more. So we wanted to think about research directions, you know, from the industry perspective. There's been an incredible amount of work done on the outcrop, which has really driven our understanding of HEB processes. But industry really concerns itself with the 3Ds, detection, distribution, and dimensions. Detection in the subsurface, that's a real problem for us. I saw in the poll that 51% of people are working either with wells or cores. And I'll be honest with you, most of us don't get that much core to work with in the subsurface either. That's a big problem. I've seen approaches that are being taken by some people at Heriot-Watt as to apply machine learning to interpret HEBs. I think that's an interesting avenue. I think probably most excitingly is if we got more into image log analysis. So there's some very high resolution resistivity tools, because I think that's our only hope. Now, at the moment, we can detect sands, we can detect debrites. Trying to detect whether they're associated genetically is more challenging. I would throw it out to academia. Get into bed with the service companies, because we would really love to get some results. Distribution, you guys are doing a fantastic job. We've learned a lot about the distribution of hybrid event beds that Jill's just been describing. We are aware that they exist in the regressive phases, sometimes in channels. Very nice piece of work by Dan Stokes recently demonstrates that point. And I cheated earlier on. One of my unconfined pieces of core from Malaysia was actually from the middle of a channel, just to show you can be tricked. Dimensionality, I won't dwell on the details here, but in industry, of course, we're always after, you know, any kind of ratios that can help inform us. And indeed, there was a question earlier on about, can the distribution of the hybrid event beds and their fascies distribution tell us something about where we are with respect to topography? And that's another key question, because that will control our reservoir distribution as well. And finally, Jill touched on this with some of the geophysical properties. Don't know why it's done that. Geophysical properties, which maybe we can take into the geophysical domain. And there's been some recent attempts at that. Finally, we could do some very interesting reservoir quality work with very high resolution fascies analysis through a scan of core in using CT. And there's a nice one here if you're more kind of greener in your leaning. When it comes to carbon capture, sequestration, and storage, you know, CO2 is notoriously easy to escape from its reservoir, and you can see in some outcrops that slurry fascies, as we see in Apennines, make actually very nice little localized seals. See, there's no fluid flow through the slurry fascies in this particular outcrop. So lots of things out there for academia if you want to have a crack at it. We will just finish by throwing out the references that we've cited there, and we wanted to acknowledge all the help and assistance the industry has got along the way through different consortia and individuals. And thank you very much.